Hayden, how's it going?
Good, how are you?
Doing all right. Were you disappointed when the Chiefs lost?
Yeah, I was. It's a sad day, sad night.
Your audio is really garbled.
Yeah, it was pretty depressing.
Oh no, sorry about that, but that's the way it goes. I'm not a huge football fan, so I didn't follow that, but I know plenty of people who are, and they were pretty disappointed.
Yeah.
Hey, Hannah. How are classes going for you this semester? Hayden or Hannah, for that matter.
They're not too bad.
Are you meeting mostly in person or mostly online?
Mostly online.
You pretty much fully adjusted to that now.
Yeah.
Well, that's good. The college is planning for in-class learning in the fall, assuming that everything goes well over the summer.
Mm-hmm.
Don't you hate it when you log on early and you plan on getting a couple more minutes of work done, and then because you logged on early, your professor just talks to you the whole time? Hey, Haley.
Hello.
Logan, how's it going? Hey, Blaine.
Good morning.
You have a hanger in your room, Haley, for your mask?
Yeah, I do.
That's like hyper organized.
I'm not organized.
we have so many different masks because we made our own, mainly so we can customize them to ourselves. For example, my mask today has bicyclists on it, and we have so many. We've given some of them away, and we also have just a basket full of masks. And there's a basket at the bottom of the stairs for fresh masks, and then there's a basket going down to the basement for masks that need to be washed. So. Hey, Jonathan, how's it going?
It's going well. How are you?
Good. Cold. All right, I think it's time, is it? Yeah, it's time. So just to tell you where we're at, we're off schedule a little bit when you go and look at the daily schedule that's posted on Moodle, but that's not a big deal. So what we're in the process of right now is going through and kind of trying to cement in you this idea of how populations are related to samples, and then how we can make inferences about samples, even when we may not have a sample size that is particularly big. And so we began last time by starting to go through the process of calculating sample, what we call sample statistics. So last time we calculated the average value, the mean value, and then we calculated the variance, and then we calculated the standard deviation. Oh no, we were talking about variance when we left off. So I'm going to do what I did before, which is basically operate off of my iPad for a few minutes so that you can see the calculations clearly. And while I'm setting that up, do you guys have any questions on kind of where we're at and where we're headed?
I mean, I take it from at least kind of what we've done so far is your plan is to explain how to do like sample variance and stuff like that, and then go back through and show us how to do it in like code and stuff and do like a math scale. I take it that's kind of where you're leading us to. Okay.
Yep. So as with everything, what I'm going to be doing is I always like people to work things out by hand first, because that's really the way in which you actually learn how something works. And then once I felt confident that we have things down working by hand, then we'll move to working things in R. So yes, that is the goal. And for whatever reason, it's not wanting to do mirroring now. Ah, there it is. I had to cancel my Wi-Fi and reload it. Okay. All right, so you guys can see my screen, right? And now I've lost you. Oh, there you are. Right. Okay, so you can see my equations that I've written. Okay. So what we did up here at the top is we calculated the mean, and then remember that you calculate variance by subtracting the mean from whatever your observation was, and then squaring that, adding all of that up, and then dividing it by 1 minus the total sample size. And at the end of class last time, I was getting across to you this idea of what a sums of squares is. So if you want to think about this, oh, I was showing you up here at the top. Here's your actual values. You observed a 1, a 2, a 3, a 4, and a 5. And then what the sums of squares is, what the numerator of the variance estimate is it's the deviation of each data point from the mean. So it's how far away is 1 from 3, how far away is 2 from 3, how far away is 3 from 3, how far away is 4 from 3, 5 from 3. But if you just add all of those up individually, they would sum to 0. So you square them so that they sum to some positive value. And then because you squared them to get them to add them up, oftentimes what we'll do is we'll then take the square root of sample variance to get what we call the standard deviation. So these are all the variance of the mean, the sample standard deviation of the mean. We're going to cover the standard error of the mean. And this just ends up being the square root of the variance. And so we would take, in this case, 2.5, which is what the variance is, and we would take the square root of that. And because I am on my iPad, we can go to the calculator, just take 2.5 and turn it on its side and get the square root, 1.58114. Okay, but what I want to do is I want to spend another minute or two on the sums of squares. So the sum of the individual values minus the mean squared, like I said before, that's called the sums of squares. This is something that you're going to see over and over and over again in statistics. And we use this in mean calculations when we're dealing with sample means, but we also use it in things like regression. So in regression, what we have generally, and we're going to study this in detail later on, you have some X variable and you have some Y variable, and you want to know if knowing something about X tells you something about Y. Well, what you get is you get an imperfect smattering of points. And then what the regression method does is it fits a best fit line through these points. But the way in which the method determines whether what the best fit line is it basically asks, how far away is this point from the line? How far away is this point from the line? How far away is this point from the line? How far away is this point from the line? These would all be on the negative side because they're below the line. And then it asks, how far is this point away from the line? How far is this point away from the line? How far is this point away from the line, etc. These are all positive values away from the line. And in the same way, if this is the best fit line, there are as many points above the line and below the line, and they're equally distributed away from it, so that if you just added up all these positive and negative values of the distance from the line, they would sum to 0. And so what we do in this case is we basically take the observed value of Y minus the predicted value of Y, which is the line, and we square that. And this becomes the sum of the squared deviations from the line. And so it's very analogous to the sum of the squared deviations from the mean. One of the ways of thinking about a regression is the regression line is just the average value of Y as X changes. And so the same idea, this idea of residual variation, this variation that's not explained by anything can be measured, is something that we'll use when we look at comparing means. It's something that we'll use when we look at estimating the slope of a line in regression. You're going to see this over and over and over again. But remember that that's just the numerator of the variance estimate. You always then divide that by the number of degrees of freedom. And for variance, the degrees of freedom is 1 minus the sample size. Okay, any questions about that? Okay, so in order to calculate a 95% confidence interval of the mean, the first thing we have to estimate is the mean. Then we have to estimate the sample variance. Then we have to estimate the sample standard deviation. The next thing that we have to measure, that we have to estimate, is the standard error of the mean. And you need the standard deviation in order to do this. So the formula for the standard error of the mean is just the standard deviation divided by the square root of n. So we know standard deviation is 1.58114. which we calculated a minute ago. And then we would divide that by the square root of 5. Once again, we can go get our calculator, and let's save that to memory and take 5. Square root of 5 is 2.3617. 2.23617. So now we can take memory recall. Whoa, that's not the memory recall. Clear all that memory out. 2.5 square root divided by 2. What was it? .23617. .7071. So this would then be this is the standard error of the mean. Well, what the standard error of the mean is for a sample mean, it's the equivalent of the standard deviation of a population. So remember back when we were looking at this population of sample means, we said that if this is the population mean, 1 standard deviation to either side, and approximately 2 standard deviations to either side. This 2 standard deviations to either side includes, in this range, 95% of the sample means. And so what we're trying to do is we're trying to build a 95% confidence interval, or for that matter, a 90% confidence interval around the mean. And the way we get that is we get that by calculating the standard error, which for a sample is the equivalent of a standard deviation of the population. But because as sample size varies, if you have a small sample, you don't really know much about the population at all. When you get bigger samples, as you saw from your homework, you have a much better idea of what the population is like. And so we scale the standard error by some measure of sample size. And we do this by looking up things in a t-table. So a long time ago, people were interested in doing things with numbers and calculating means and then making decisions about those means. And there was a guy who actually worked at the Guinness Brewery in England, in Ireland. And he wanted to have a way of looking at the statistics that were coming out of the brewing process and figuring out how to actually compare these to one another as variation in brewing batches occurred and things like this. And because he was under contract with Guinness, he wasn't allowed to publish any of the work that he did for Guinness because it's proprietary. But he thought that this was important enough that he wanted to get it published, and so he published this thing that he invented called the T Statistic. And you will sometimes call it just referred to as the T Statistic, or you'll sometimes call it referred to student's T. And the reason it's called student's T is this is the name of the dude who published it, the author of the work. But that's not actually the person's real name. He adopted the pen name student so that he could publish it, so that his employers wouldn't know that he was publishing this thing that he invented while he was on the clock at the brewery. And so what the T statistic is it's basically just a way of thinking about how does your confidence in your estimate of the mean vary as sample size varies? So if you have a small sample size, like a sample size equals to 2, you're not very confident in your estimate of the mean. As a result of that, your 95% confidence interval of the mean has to be wide in order to ensure that you capture the population mean within that range, because you don't have a very good idea of where that population mean might be. And we saw this when we looked at our card draws at different levels of sampling intensity. When we got up to a sample size of 30, we had a pretty darn good idea of where the population mean is in all of that. If you have a large sample size, let's say n equals 30, you have a much better idea of where the population mean is. You're very confident in that. This is why we call them confidence intervals. And so the 95% confidence interval can be narrower because you have a better idea of where the mean is. And so he created a set of values for the T statistic. So if you just go to the internet and look up a T table, you will see something that looks like this. Well, that was my preferred version. Why? Why are you not letting me access? Okay, so we're going to look at the two-tailed probability, because the two-tailed probability gives us the 95% confidence interval. So down here, it shows you the confidence interval. You can calculate a 90% confidence interval. You can calculate an 80% confidence interval, but pretty much the standard practice is to begin with a 95% confidence interval. And what you see down here is at the bottom, if you have an infinite sample size, the 95% confidence interval value for T is 1.96. If you go out 1.96 standard errors of the mean, you are at a 95% confidence interval. But if you only have 2 samples, you have to go out further away from the mean to be confident that the population mean is going to be in that interval. And if you only have a sample size of 2, if you have 2 degrees of freedom, which would be a sample size of 3, it's 4.303. If you have a sample size of 2, which means you have 1 degree of freedom, it's 12.71. So the thing that you multiply the confidence interval by is much greater when you have really small sample sizes. When you get up to a sample size of 30, that thing has fallen to 2.042. Sorry, a sample size of 30 would be 29 degrees of freedom. It's 2.045, which really isn't that far from 1.96. And so a professor that I had in statistics when I was in graduate school said to the class one day, 30 is a lot closer to infinity than it is to 0. And what he means by that is that by the time you get up to 30, a sample size of 30, which would be 29 degrees of freedom, you're much closer to the T value for infinity than you are to the T value for a sample size of 2. And so you've really, at a sample size of 30, you've really got a sample size that is big enough such that you can feel confident that you know quite a lot about the population that you're drawing that sample from. And it's under those conditions that you're going to be able to utilize the central limit theorem and the power that that gives you best, because it's under those conditions when the distribution of sample means is going to be nice and normal, and that these percentages in terms of the wanting to encompass 95% of the sample means is going to be most applicable. So remember that what we're doing is we have a population, and on your homeworks, which I've been grading, I think I have 2 left to grade, and then I'll probably be sending those back out to you via email later on today. It was a 25-point 25-point assignment, and most of you got full credit, even if there were some minor mistakes. But one of the things that is recurring in those homeworks as I look at them is you don't have a clear idea of what a statistical population is. So can somebody tell me kind of their best definition for what a statistical population is? And if nobody speaks, I'm just going to pick somebody at random. So you might as well just talk. Hannah, go ahead, because I thought I saw you reaching for your spacebar to unmute yourself.
Isn't it kind of, or isn't it like a like taking data from a specific group and getting all of their data?
Okay, so you're usually trying to know something about the statistical population, and we know something about the statistical population by basically drawing a sample from it. So imagine that you are, imagine that you're a student and you're working at the beer factory and you're brewing batch after batch of beer. And what you want to know is you want to know what the alcohol by volume is. If you guys ever pick up alcohol, which I'm sure you don't because you're good Joule students, right? Yeah, exactly. If you ever pick up a bottle of beer or a bottle of wine or something like this, or rum or whatever, it will have an ABV value on that bottle. And the ABV value is the alcohol by volume. Do you guys know how alcohol by volume gets calculated? One way that you can calculate it is you can calculate it actually by using instrumentation to measure how much alcohol is in a particular volume. But home brewers, do any of you guys brew at home? I make mead. It's one of my hobbies that I do. Mead is basically fermented honey. It makes a nice light wine when you haven't fermented it too long. Well, in home brewing, you basically take a flask, a tube that holds liquid, and you fill that with whatever your liquid is at the beginning of the brewing process, and then you put a type of instrument in there that measures the specific gravity of your fluid. And the specific gravity of honey, for example, honey mixed with water and yeast, is largely determined by sugar content. And as the yeast go through and digest that sugar, the byproduct that you get out of that mixture is alcohol. So you take sugar, you expose it to yeast. As the yeast use the sugar for metabolism, the waste product that they produce is alcohol, and that's how fermentation operates. And so what happens is the specific gravity at the beginning of the brewing process is quite high. So there's a little scale on this where the scale matches up with the top of your line of the fluid. You read off what the specific gravity is, and it's quite high because there's a lot of sugar in here, which is supporting the buoyancy of this instrument that you've dropped into there. As you continue the brewing process, there's less and less sugar because that sugar has gotten used by the yeast, and this thing sinks further and further down there, and so your specific gravity actually decreases over time. And then the difference between what the specific gravity is here and what the specific gravity is here, you can then calculate based on that change in specific gravity, how much of that sugar has actually been converted to alcohol. From that, you know how much alcohol is in the volume, and so then you can calculate the amount of alcohol per unit volume. So you can do this using home brewing sorts of methods if you're brewing your own beer or brewing mead or making wine or something like that at home. You would do this differently if you actually worked at a brewery. You would actually do it with an instrumentation that does this electronically. But one of the things that you want to do when you're making mead or beer is you want to have a very consistent amount of alcohol by volume. So when I first made my first batch of mead, I let it ferment too long, and it basically, the yeast used all of the sugar, converted all of the sugar into alcohol, so it ended up being like 13% alcohol by volume, which is way too high for mead because it lacked any of the sweetness that you would normally associate with mead. It just basically really tasted like you were drinking honey flavored alcohol. And so the flavors were there, but it was just really too alcoholic for my taste. And so what I have to do with my next batch of mead is I need to shut off the fermentation process. So let's imagine that your student, the guy at Guinness who invented the T-test, and you want to know what the alcohol by volume is of different batches, but you're actually interested in what's the alcohol by volume of every batch of beer that Guinness produces. But rather than measure every batch of beer that Guinness produces, you can sample periodic batches, and over time you have a sample. You have a sample of that broader population of the beer batches at Guinness, and then you can get some idea of what the average alcohol by volume is, and you can also get some idea of how much variation there is from batch to batch of that. So in this case, what would be the statistical population? Somebody other than Hannah.
All of Guinness's beer?
All of Guinness's beer. All of Guinness's beer, not only that they've ever produced, but also all batches of Guinness of beer that they will produce in the future. That's what student is interested in. What is the alcohol by volume content of batches of Guinness? Now, you can't measure that because some of those haven't even been brewed yet. But what you can do is you can get a sample of those and get an estimate of what that population level value is. But it's going to be imperfect because you're not measuring every batch of beer that comes out necessarily. And as a result, you want to have some degree of confidence as to whether your estimate of the alcohol by volume actually matches up to the population mean of alcohol by volume. And so in order to do that, you need to know what your sample size is, because as your sample gets bigger and bigger, you have a better and better idea of what's going on in the population. As your sample size gets smaller and smaller, you have a less clear view of what's going on in the population. And as a result, your confidence is lower. So to create an interval of ranges around that mean that gives you confidence that somewhere in there is the population mean, that then has to be much bigger. So when we go and look at this for the sample that we just looked at, we had a sample 1, 2, 3, 4, 5 individual values. So that would be degrees of freedom of 4. So when we look at the 95% confidence interval for 4 degrees of freedom, the T statistic that we would have to use is 2.776. So to calculate, the 95% confidence interval, we would take the average value, which we measured as 3, and we would add to that and subtract from that the T statistic multiplied times the standard error of the mean. So in this case, we know that the standard error of the mean is 0.7071. And we would multiply that times whatever the T statistic is for a particular alpha level. And at our point, it's going to be an alpha level of 0.05, any particular degrees of freedom, which in our case is 4. It's an alpha level of 0.05 because we're testing at a 95% confidence interval, and 100% minus 95% is 0.05, okay? So if we convert these to decimals, 1 divided by 1 minus 0.95 is 0.05, and that ends up being the alpha level. We're going to talk a lot about alpha level at the end of class today and into Friday. So what we do then is we go and we say, all right, well, we need a t value at an alpha level of 0.05 and 4 degrees of freedom, that's 2.776. So this would be 3 plus or minus 2.776 times 0.7071. .776 times 0.7071, that's 1.963. 3 minus 1.963 is 1.037. 1.037. This is the lower limit of the confidence interval. And then we can go back to 3 minus, oh, what was it that I did? 2.776 times 0.7071 plus 3, so that would be 4.963. So what the confidence interval basically means is that the mean, the sample mean, is between 4.963 and 1.307. But because this range is the 95% confidence interval, one way of thinking about a 95% confidence interval is that we know that somewhere in this range, the population mean is also there. Now, we don't know where the population mean is. It's just that there's a 95% probability that it falls within this range of values. So that's one interpretation of what a 95% confidence interval means. So one way of interpreting a 95% confidence interval is to basically say you have a 95% chance of finding the population mean somewhere in there, if you're actually interested in what the population mean is. The population mean is probably not the sample mean, because the odds of stumbling upon the population mean with the sample is actually pretty unlikely. But one way of thinking about the confidence interval is we don't know what the population mean is, but we're pretty sure that it's somewhere in this range. It could be, if this is on a number line from 1 to 5, and so this is 4.963, and this is 1.307. Our sample mean was here at a value of 3. Now, it may be that the population mean is 3, but it could be the population mean is above 3, below 3. It could be above 3 or below 3, really far away from 3, but we have some confidence that somewhere in this range of values, there is the existence of the population mean. Now, the population mean could be way out here, 5.2. But there's a relatively small chance that it's out there at 5.2. It could also be over here at 0.5. But once again, there's a very small chance that it would be out there because we have made our confidence interval wide enough based on our sample size to have a confidence that it is in this range. But that's not the only way in which we can think of what a 95% confidence interval is. And it's the second way that I'm actually going to be referring to primarily. Another way is this way. Give me a minute to write this out. Another way of thinking about the 95% confidence interval is if you go to this population and pull 1,000 samples of size 5 out of the population that we drew these numbers from, 950 of the sample means should fall within this range. Now, 50 of them will fall outside of that range, but 950 of them should fall within this range. And in statistics, seldom are people trying to estimate what the population mean is, but oftentimes in statistics, you're interested in comparing one mean to another mean. So let's say that student worked at the Guinness Brewery for 50 years. He might be interested in if the alcohol by volume of the first 10 years of batches is different from the alcohol by volume of the last 10 years of batches. And so what he would be interested in is not what is the actual population mean. He's just interested in, does this 10 years worth of samples differ from this other 10 years worth of samples? Has something about their brewing changed such that there's been a change in alcohol by volume over time? And because these things would creep up on you, they would change slowly over time. You might not notice them if you were just going sampling, but if you looked at a snapshot at the beginning and a snapshot at the end, you might see that difference. So oftentimes, what statisticians are being asked to do by people is they're asking statisticians to compare means to one another. So even though this is a perfectly appropriate way of thinking about what a confidence interval is, seldom are you being asked to make inferences about what the population mean is. So even though this is appropriate, this is what you find yourself doing most often. And so this is probably a more productive way of thinking about a sample mean from a practical, pragmatic standpoint. All right, I've now talked for like 24 minutes, which is much longer than I should talk. Do you have any questions about how to go from a mean to a 95% confidence interval? Okay then, wherever you're at on your, I'm working on my iPad. So I invented this data set, this first data set, which had a series of X values that were just 1, 2, 3, 4, and 5. This had a mean value of 3 and a 95% confidence interval that goes from 1.307 to 4.963, right? Yep. So what I want us to do now is take another data set that I just totally made up, 2, 4, 6, 8, and 10, and I want you to calculate the mean, the variance, sample variance, the sample standard deviation, the standard error, and the 95% confidence interval of the mean. Now, before you start doing this, just based on the numbers themselves, what do you expect to be happening with the mean and the 95% confidence interval of these data, just based on the data compared to the first set of data? Is the mean going to be different numerically? Yeah, why?
A different set of numbers.
Okay, so for one thing, it's a different set of numbers. Also, these numbers differ by 2. So the low value and the high value are further apart. So because the high value is further from the low value, then you can expect this mean is probably going to be larger. What's going to happen to the variation? So things like variance, standard deviation, standard error, all that. Are those going to be similar, or are those going to be different? Haley, stop working. Answer my question.
Sorry, I was still writing everything down.
Oh, okay. All right. Well, since you're unmuted, what do you think is going to happen to variation? Is variation higher or lower in this sample?
I'm gonna say higher.
Yeah, it's more variable, isn't it? So whenever you look at a set of numbers, there are a couple of things that you can just intuitively gain from those numbers just by taking a quick glance at them. In these numbers, you expect the mean to be higher, and you would also expect the variation to be higher, which means that the variance will be bigger, the standard deviation will be bigger, the standard error will be bigger, and the confidence interval will also be bigger, not because you have a different sample size, but because the data themselves are more variable. So let's take a couple minutes and work through this. I'm going to hide my screen so that as I do my work, you can't see what I'm doing. Put your little raised hand icon up when you're done with your calculations. Still working? Some of the values you already have. So for example, you already have the square root of sample size because sample size is the same for both of these things. And also the T statistic that you're going to use is also the same. So it's 2.776. So I finished my calculations. You can also feel free to ask questions if you're having trouble with any of the calculations as you go through.
I'm trying to work on the confidence interval, and
Yeah.
you mentioned that the t value was what again? And I'm confused because when I'm looking at my notes, it says for when we calculate it, it says 3 plus or minus 0.05 times 0.7071, and that would
No,
be
no, the 0.05 is the alpha level. So you're looking for a T statistic. And the
okay.
T statistic for an alpha level of 0.05 is 2.776 at your sample size.
0.776.
Yeah,
Okay,
so it would be 2.776 times whatever the standard error is. Now your standard error is going to be different for this data set because it's a different data set.
right. And I believe I've calculated that. I was just having troubles on the very last calculation.
Yeah, that's fine.
Okay, perfect.
Yeah, good. So Blaine, since I was doing mine in a note-taking app, I was able to just go back and say, oh, well, what's the T statistic for this sample size and an alpha level of 0.05? Well, that's the thing that I'm looking at for the T statistic. And also when I was calculating my standard error, I'm like, well, I've already calculated what the square root of 5 is. That's 2.23617. So I didn't recalculate that. I just went back a couple of pages and got my result. All right, Logan's done. Who else is done? Blaine is done. If we were in a classroom, I would be walking around the class, looking over your shoulder, looking at your calculations as you go and fixing things that I saw were going wrong. Obviously, I can't do that here. Which is why you need to let me know if you're having troubles with any of the steps.
What was the last calculation after standard error? We were supposed to do?
Sorry, Hayden, I can't understand you. You're coming through, but I can't. It's garbled.
After the standard error is just the confidence intervals, right?
Yep.
I think I'm confused on how to get the confidence interval.
Okay, so in this case, our average was 3, and then we're going to add to that whatever the T statistic is and whatever the standard error is, and we're also going to subtract whatever that is. So it's 3 plus or 3 minus. Now, in this case, it's going to be 6 because the mean is 6 in this case. So it's going to be 6 plus 2.76 times whatever the standard error is, and 6 minus whatever 2.776 times the standard error is. And that gives you these boundaries. And now I just pulled it away from you. What?
Sorry, where did you get the 2.776?
I got that from the T table. So
Oh, okay.
if I go back to here, we find an alpha level of 0.05 or the 95% confidence interval. So in this column, we go down to degrees of freedom equals 4, and at 4 degrees of freedom and a 0.05 alpha level, that's 2.776. And it's the same one that we used before. So rather than go back to the internet and look that up, I just used the value from when we did it for the other data set.
Okay. Thank you.
The same value. Once I've done, just like calculating the denominator in the standard error, rather than going back and recalculating what square root of 5 is, I just try and avoid recalculating things that I've already recalculated. It saves time. Hayden, did you get it done? Raise your hand. I can see the others are clearly still working, but it just helps me keep track. Like I said, easier to do this kind of thing when we're in class and I can actually walk around and see you still working. Jonathan, you done? Hannah,
And
okay, I see the thumbs up.
we're done. Is that correct?
What's that, Jonathan?
We're gonna go through these and how we got the answers. Is that correct? And
Oh
we're
yeah,
done?
yeah, I'm just waiting for everybody to get done.
Okay, good.
Yeah. No spoiler alert. Yeah, I'm done on the next page. I showed it to Hannah for just a sec. So yeah, when everybody's done, we'll go through it. Hannah, are you finished? Yeah, you are. I saw a thumbs up earlier. Okay, all right. Okay, Haley's done, so we're waiting on Samuel and Chance, I think. Is that right?
Yeah, but I am confused and I don't know what questions to ask, so don't wait on me, please.
Okay. Where are you at? Where are you stuck in the process?
Last class, I didn't start taking notes till this class, so I'm a little behind, I feel like.
Okay,
That's
all
why.
right. That's why you should go and review the video.
Hindsight's 2020, you know.
Yeah. Well, that's actually the nice thing about having those videos loaded up is that you can always go in and get those before we meet next. Yeah, I just kind of started in on like, oh, this is where we left off. But yeah, okay. How are you doing, Samuel?
Same. I'm like getting towards the end, but I'm a little confused. So.
Okay. All right. Well, then let's just go ahead and go through it. So Hayden, what did you get for the mean?
Six.
Okay. Blaine, what did you get for the variance?
For the variance, I got variance is s squared, right?
Yep.
I got 9. Is that incorrect?
That is incorrect. Logan, what did you get for the variance?
I got 10.
Okay. Did you then divide that by the sample size? Because 10 is what the sum of the squares is.
Oh, so it should be 2.
Logan?
What?
Was that the sums of squares that you gave me, or is that the sample variance?
The variance.
What did I get?
I also got 10.
Oh, I got, yeah, I wasn't showing you my own work, so I couldn't see it. So yeah, sorry, variance is 10. So yep, variance is 10. So the mean is 6, the variance is 10. Did you guys all get 3.1623 for the standard error? Or sorry, standard deviation rather? Yep. So then that should have given you a standard error of 1.4141. Okay. So Samuel and Chance, so the way we did this is we calculated the mean, first of all, over here. And then, sorry, no, that's not the mean. Go back. That's the mean from the first set. We calculated the mean by adding up all the values and dividing them by the number of values that we have. That gave us a mean of 6. Then we subtracted 6 from each of the values, which gave us -4, -2, 0, +2, and +4. We squared each of those things, and then that gave us 16, 4, 16, 4, and 0, which sums to 40. When you divide 40 by 1 minus the sample size, that gives you a variance of 10. The square root of 10 is then 3.163, and then that divided by the square root of n is 1.4141. So these are just the steps that we go through. Once you have that, you multiply that times the T statistic for whatever level of confidence you want and whatever your sample size is, and then you add that to the mean and you subtract that from the mean, which then gives you the mean sitting in the middle. And then did you guys get 9.9255 for your upper limit and 2.074 for your lower limit? Okay, all right. So what I've done down here at the bottom then is I've just basically put these two things on a number line. And so here's the mean of 6 for the second sample, the mean of
Dr. Kowinski,
yep.
we've lost your screen, or at least I did.
Oh, crud. We did lose the screen. That's weird. Thanks for telling me that. Let's see. Go to screen mirroring. I've been having trouble connecting to Wi-Fi, and the screen mirroring thing works with Wi-Fi. Okay. So I've just made a number line down here where you can see the mean of 6 of the second set and the mean of 3 of the second set. And then I've just crudely drawn what the confidence intervals are. Now, if we want to know if this mean is different from this mean, what we basically ask ourselves is, could we have drawn this mean from the population that we drew that mean from? So we ask ourselves, could this mean have come from this population's mean? And because this mean is within this population's, this sample's confidence interval, we could have easily gotten this mean from this mean's population. But we can also ask, does this mean fit inside of this mean's confidence interval? Could we have drawn this mean by drawing it from the same population as this one? But because it falls outside of that confidence interval, we would conclude that you couldn't do that. So we'll talk more about this decision-making criterion on Friday. Two things I want you guys to do is on the Moodle site, there's material. I think it was from Monday, but it might have been from Friday. It's the last set of materials that I uploaded. There is a data file called loveit.csv in there. It is data on sulfate levels and chloride levels and other things, but there is a column called SO4, which is sulfate, and it's divided into low elevation sites and high elevation sites. Just practice homework for Friday. Calculate the mean, the variance, the standard deviation, the standard error, and 95% confidence intervals for sulfate levels for low and high elevation sites in that data file. And then bring that with you at the beginning of class on Friday. Then the other thing that I want you to do is I want you to read section 3.2 from your textbook. This is the section that deals with type 1 and type 2 errors, because we're going to talk about that on Friday. Okay? Questions? All right, if you have any questions about the mechanics of doing this, I'm going to see how, one of the reasons I'm taking this in a note-taking app and doing this is because I think you can see the screen clearer than you can see the board in my office. The other thing is I can take these things hopefully and just download them as like PDFs or something. So I'm going to see what I have to do that, and I'll post these notes that I've been keeping for the last couple of days to the Moodle site as well, so that those of you who missed class on Monday can go through the mechanics of what we did. Okay. All right. Then if there are no questions, I will see you guys on Friday.
Thank you.